Thanks for the introduction. Good morning, everyone. I'm very glad to be here to talk about our work on exploring spike encoder designs for near-sensor edge computing. So this work is mainly done by my students, Jing Gang and Zhen Hang. And this is the outlines. So basically, I will talk about introduction and motivation, and then our method, and followed by experimental results, and finally will be the conclusions. So basically, the emerging cyber-physical systems and the embodied AI calls for lots of edge capabilities. So these applications basically include continuous sensing, monitoring, detecting, and responding to temporal and sequential patterns in physical environment. And those systems requires low cost and also small footprint and also high energy efficiency. And at the same time, flexibility and adaptability are also important to the users and applications. So neuromorphic computing obviously offers a very promising solution by leveraging spiky neural networks. So with SNNs, information are represented using sequence of spike trains. And the neurons communicate and compute with each other only when there's incoming or output activities. And such event-driven approach basically provide, combined with closely integrated memory and computing, provide very high energy efficiency. So, and to effectively utilize the spiky neural network, the input signals must be encoded into spike sequences. So which means we need to sparsely project input temporal sequences into hyperdimensional feature space and or feature vectors distributed evenly across the feature space for better separation. And so basically, our system considers an input with basically multi-channels of sensor readings. And after the encoding, the analog sequence will be converted into spike trains and finally being processed by an SNN-based classifier or processor. And we refer to this encoder as front end and the classifier as the back end. So a well-designed spike encoder should be able to convert numerical sensor reading into sparse spike trains, and also preserve the temporal and spatial features in the input space. And they should be built with very low-cost hardware, simple operations, and with minimum memory usage. So there are two typical ways to encode the spike. One is called a spike rate encoding, and the other is the spike temporal coding. The spike rate coding basically the encoder periodically samples the input sensor reading and convert it into high precision floating point numbers. And then this numerical value will be converted into spiking activities. And the value is represented by the spike count generated within the sampling interval. So as we can see that the maximum possible spike count actually determines the highest achievable data precision. And this type of encoding usually generate a high spiking activity and hence a high energy consumption in computing and communication. And the spike temporal coding can be further divided into two different types. One is the spike interval coding, and which basically encode input values as the interval between the consecutive spikes. And the other type is time to first spike coding, which basically encode the interval as the time delay between a spike and a reference starting time. So for both of them, at most one spike event is generated for each sampling interval. Therefore, they basically correspond to much sparse communication and computing. So in this work, we focus on spike interval coding. And in our previous work, we used the CUBA neuron or current-based leaky integrated and fire neuron to encode the spike interval coding. The CUBA neuron basically performs leaky integration of the input X And then the membrane potential is then converted into output using this heaviside activation function. With the Cuba neuron, basically when the input value is low, the interval between the two spikes basically is larger. And when the input value is high, then the spike interval is smaller. In this way, we can achieve adaptive spiking rate. However, the traditional way to encode the spike sequences has some limitations. First of all, they match each channel of sensory input to one spike chain, and this type of one-to-one mapping cannot effectively preserve the spatial and the temporal features. First of all, not every sensor's reading will be falling within the sensitivity range of the leaf neuron. If the sensor reading is too low, the neuron probably will not be able to generate a spike for a very long time. And if the sensor reading is too high, then the high value will be cropped. And secondly, very subtle differences between sequences has to be accumulated for a very long time before they can make different at the spike output. And in addition, the traditional approach basically used the sensor encoder to collect sequences and then use this training data for offline training. And it is difficult to guarantee that the training data set provide an accurate representation of the testing data because if the encoder is implemented using analog or mixed signal, then significant device-to-device variation exists, so that it's hard to guarantee the testing encoder is the same as the training encoder. And furthermore, the front-end sensor and the back-end processor usually operate at a different clock asynchronously. So we cannot assume any predetermined timing relationship between the sampling clock and the classifier or back-end clock. So in this work, basically, we try to address these limitations. First, we design two new spike encoders. One is, we call it population coding-based encoder, or POP-INC. The POP-INC is a layer of leaf neurons fully connected to the sensor input. And then we compare the performance of optimized POP-INC and random POP-INC. The second type of encoder is reservoir encoder, which is inspired by the reservoir computing model. And then we enhance this reservoir encoder by adding skip connections. We also train the encoder together with the back-end classifier so that we can adapt, so that the classifier can adapt to the encoder. So basically for the population encoder, it's a set of leaf neurons with postsynaptic potential. So each postsynaptic potential is represented as a first-order IIR filter. And the synaptic potential is calculated as using its previous value plus the weighted input value. And then the membrane potential of this neuron basically is a leaky integration of the weighted PSP, or postsynaptic potential. We use N neurons to jointly encode M channels of input. And we have, again, two versions of POP-INC. One has optimized the W and the filter kernel. The other has random weight and filter kernels. And for the reservoir encoder, so basically we assume there are I input channels and the J neurons form a complete directed graph. So the neuron state of these internal neurons is denoted as X. The X is updated based on its previous value and the input value, weighted by the weight matrices X, WX, and WIN, and also a bias. We assume the bias is drawn from a uniform distribution with the range from 0 to 1. And the two weight matrices are random matrices following also uniform distribution in the range of epsilon to positive epsilon, where epsilon is a value determined by the fan-in and fan-out of the postsynaptic neurons. And also, we added some refractory mechanism so that the output of each reservoir neuron will go through the refractory mechanism function, such that when it fires at current cycle, then it's less likely to fire in the next cycle. And after that, each neuron also goes through a heaviside activation function to be converted into the spike activities. And so both pop-inc and reservoir encoder are stateful network. The neuron has memory to memorize the previous input. The limitation of those stateful encoder networks are like, because of the recurrent structure of the network, it may take a long time for the change in the input to affect the output spiking activities. And for example, for sequential data, especially long sequences, the memory of the early input may prevent the later input to change the output until we wait for a long time. So to avoid such limitation, we added skip connections. So the skip connection basically is a direct connection from the input to the output. The only processing is the heaviside activation. So with the skip connection, we have two sets of output. OX, which are the output from the stateful neurons, and OU, which are the output from the skip connection. And the backend classifier basically is based on spiking neural network. So these are multiple fully connected layers. Each layer are composed with neurons, which are similar as the one we used for population encoder. These are live neurons with the postsynaptic potential. And we also adopt online learning SALSA learning algorithm, which we developed in our previous work to online learning. The benefit of using SALSA is it does not have to unroll the network over time. So it uses very limited memory and it can fit on the on edge devices. So this is a very quick introduction of how SALSA works. So SALSA basically combines the backpropagation with the three-factor Hebbian learning. At each time, the L2 error is calculated by comparing the classifier's output with the expected output. And the weight is updated using this rule that the EDW is calculated as the summation of mu and epsilon. Mu is basically the upper level gradient backpropagated from the input-output layer to the input layer. It can be decomposed into this way, and actually each term is neural network parameters such as alpha, which is the synapse filters coefficient. W is the weight coefficient. And these two lunar epsilon are a surrogate gradient of the heaviside activation function of the neuron. And the epsilon basically is a local trace which stores the history information. It can be updated incrementally. And epsilon is updated using this function. It's based on its previous value and the postsynaptic potential, and together also considering the lunar epsilon, which is the surrogated gradient of the heaviside function. So using the SALSA, basically every time step, we calculated a partial gradient, mu times epsilon, and accumulated it. This means we don't have to wait until the end, until we receive the entire input sequence, then to update the model. We can update the model using the partial gradient in the middle when the input sequence is still going on. So this actually accelerates the convergence of the learning significantly in our previous work. We found. And so we also mentioned that we use a surrogate gradient function for the heaviside activation. So we actually use the gradient of the spiking probability as the surrogate, which is listed here, that I'm not going into detail in this talk. So with the experiment, we evaluated our basically encoder using 7 data sets. So all of these data sets are multivariate time series. And the sequence length of the data set varies from 30 to 1,000 time steps. And this table actually listed the number of input channels and the number of classes we need to classify. And these data are basically collected from sensors such as motion sensor or EEG sensor or acoustic sensors. And so in our experiment, we compared 3 different types of encoders. One is the random pop-inc population encoder, which basically its weight and the synaptic filter kernels are both optimized using our SOSA algorithm learning. And the second one is, random is not optimized. Their weight and the kernel are random selected. And the optimized population encoder has weight and kernel optimized using the SOSA learning. And the third one is reservoir encoder, which also has randomly selected weight and bias. And as a reference, as a baseline, we also created a long short-term memory, which is a pure ANN, with similar complexity as our spiky neural network-based classifier. And the LSTM has 1 LSTM layer and 1 fully connected layer. And in terms of complexity, basically, we refer to the number of trainable parameters. However, it is very hard to make the 2 models to have exactly the same trainable parameter. So we created 2 LSTMs. One has slightly smaller size than the SNN. The other has slightly higher size or complexity compared to the SNN. And we need to note that the LSTM assume that front end has a high precision and analog to digital converter. So it receives the floating point input. And we first compare the performance of our encoder with the LSTM. So this chart shows their performance in terms of the classification accuracy. The first 2 bars, the blue and the green bars, refers to the performance of the 2 LSTM, and the last 3 bars refers to the performance of our encoder, with the yellow bar represent the random population encoder, the purple bar represent the optimized population encoder, and the orange bar represent the reservoir encoder. And as we can see that, so our spiky neural network-based approach almost provide comparable or superior performance than the LSTM. And as we expected, of course, the optimized population encoder also performs the best. However, even the random population encoder also the performance is also quite acceptable. And in the second experiment, we show the impact of skip connection. So we created actually a baseline approach, which has only the skip connection without any like stateful neurons. Its performance is represented by this blue bar. As we can see, with only skip connection, the performance is not stable. So which means directly using the input is not basically a good or a feasible approach for the spiky encoder. However, we can also see that, so in this, the green bar and the purple bar are the random population encoder and the reservoir encoder without skip connection. And the yellow bar and orange bar are their similar versions of encoder with skip connections. As we can see that by adding the skip connection, we can improve the classification accuracy by 4% to 3%, so which shows its effectiveness. And we also compared our reservoir model with some traditional reservoir models. First, for their complexity. So basically, this table shows the number of connections, the number of neurons, the memory usage, and the activation function compared between our reservoir model and some traditional models. We can see that our reservoir model has fewer number of connections and also fewer number of neurons, and also much simpler activation function. And this chart compares the performance when they're used as the encoder. The performance is again measured by the classification accuracy. So the blue bar is our reservoir encoder, and all the other bars in other colors represent the performance of other reservoir models. As we can see, even we used a simplified architecture, the capability of our encoder in terms of preserving the temporal and the spatial features actually does not degrade compared to other models. And the last experiment actually shows how important adaptability is to the hardware variations. In the first experiment, the hardware variation comes from the random weight in the reservoir encoder. So we created 3 different versions of the reservoir encoder by sampling different weight coefficients. And for each encoder, we trained a back-end spiking neural network classifier. And we tested this classifier using the 3 different test encoders. So, and this basically chart shows the accuracy under different testing and training combinations for different data sets. As we can see that the diagonal entries, which corresponding that the testing and training encoder are identical or similar, basically gives the best performance, while all other entries has actually much lower classification accuracy. So basically, when the classifier and the encoder do not match with each other, the performance drops significantly from around 15% to almost 80%. So it shows the importance of adapt the classifier together with the encoder. And the last experiment shows how the adaptation is important to the frequency variations. So basically, we sampled the, so basically we have an encoder and we trained a classifier using nominal sampling rate. And then we also, in the testing environment, we vary the sampling rate from 50% to 150% of the sampling of the nominal sampling rate, and create different sampling, create different testing cases. And 4 different systems are tested. The first one is a population encoder with both adaptive front end and back end. The second case is population encoder without any capability of adaptation. And the third and fourth cases are the LSTM models without adaptation capabilities. And these charts shows the comparison of performance for different systems, those 4 systems under different sampling frequency. So different colored bar represent the different sampling frequency for different training data set. So as we can see that in extreme cases, this offline non-adaptable systems can have performance drop up to 8.3% compares to the case systems with adaptability, which only drops 3%. However, it's actually to our surprise that this system can adapt to the frequency variation quite well, all of them, compared to the hardware weight coefficient variations. So as a conclusion, so in this work, we proposed the new spike encoder designs. One is population-based encoder, the other is reservoir-based encoder. So our experimental results shows that the encoders can effectively preserve the temporal and the spatial features. And we also showed that adding skip connections can also improve the performance of these encoders. And also, we showed the importance of adapting the back end and front end together, which can provide significant improvements of the classification accuracy. So with this, I conclude my talk and ready for questions.